All right, so with carboxylic acids, they can undergo a number of reactions. So these are very reactive molecules, and the first thing we want to talk about is the fact that, well, they're acids. In their name it says carboxylic acid. So as we know, acids are proton donors. So you have your carboxylic acid, which can donate an H. So right there is an H that can be donated. Now there are going to be other H's attached over here to the R group. Remember that R group might be like a CH2, CH3 or something like that. The specific proton that's donated in carboxylic acids is the one attached to the O. So whenever you have the OH in the carboxylic acid, that's going to be your acidic proton, meaning that's going to be the proton that's removed and is donated. So again, carboxylic acids are proton donors, so they're going to act as an acid, which means that whenever you come to the other side here and you look at this carboxylate anion, that would be the conjugate base. So this here would be your conjugate base. So if you were to put a carboxylic acid in water, water would act as a base, and then it would form the conjugate acid, which would be H3O+. Now, whenever we talked about acids and bases, we defined weak acids as acids that only partly dissociate in solution. In other words, you might have 100 molecules of a particular weak acid in solution, and 99 of them are not going to dissociate, and maybe only one of those 100 would dissociate. So carboxylic acids are considered weak acids because they do have this property of only partially dissociating in solution. So if you were to add a carboxylic acid to a solution, most of it is going to stay in this form where you have the OH on it, and you're only going to have a very small amount that dissociates into the carboxylate anion, which you can see over there. All right, so in the previous slide, we looked at the reaction of a carboxylic acid with water. Carboxylic acids can also react with bases, right? Acid reacts with base, and particularly whenever you react with a hydroxide containing base like NaOH, you're going to form water. So in this case, you're going to have the OH from the base, and you're going to have the H from the acid. Those are going to come together, and they're going to form water. And if you remember, whenever we had an acid and a base back in chapter 8, and we talked about this reaction, it was an acid and base formed water and a salt. Well, this sodium acetate here is going to be our salt. So a salt, if you remember, it's a cation and an anion. That cation is going to be the Na+, and the anion is going to be this CH3COO-. That's going to be the acetate ion. All right, so the acid plus base forms water and a salt. Same reaction we've looked at in the past, except this time it's just a little more complicated of a structure whenever you're over here looking at your carboxylic acid, which is the acid. So these reactions are actually somewhat useful in kind of like medicinal chemistry and other things like that, because you can actually take solids or things that are water insoluble, I should say. Something like octanoic acid down here is water insoluble, which you might be wondering, well, how is that water insoluble? Because if you think about it, it's going to be polar, and more than that, it does have the ability to hydrogen bond. Right, you have an H that's bound to an O, N, or F. So octanoic acid can hydrogen bond. So this is where I have to tell you that, like in the earlier part of the class, whenever we said that anything that can hydrogen bond is water soluble, I was kind of exaggerating a little bit, and I was just kind of getting that in your head. At this point now, some of the molecules get a little more complicated. And if you look at something like octanoic acid, there's a large part of octanoic acid over here, right, which is very nonpolar. Then you have a region over here which is polar and can hydrogen bond. And there's some point where kind of the nonpolar part wins out. And we'll talk more about this whenever we talk about lipids in a couple chapters. But in this case, octanoic acid is actually an insoluble molecule. You don't have to know necessarily like at what point these turn into being insoluble versus soluble, as far as I'm concerned. As long as you know that something that can hydrogen bond is water soluble, that's a good thing. But we'll talk about as you get kind of these more involved kind of structures that have longer hydrocarbon components like there is in this octanoic acid, that they definitely can also be water insoluble. But the reason I talk about all this is you can actually take something that's water insoluble and undergo this acid-base reaction where this proton is going to react with that OH, and that's going to go and form your water. And then you're going to have your salt, which is going to be left in these components left. Salts are always going to be water soluble. So if you have a salt where you have a cation, that would be your cation. That's going to be your anion. Whenever you have those two components, that's always going to be water soluble. Carboxylic acids and esters both undergo a number of reactions, and all the reactions that we're going to look at can be classified as these substitution reactions. So a substitution reaction is this general name for the reaction where you're going to have either a carboxylic acid or ester, and that's what we're looking at on this side of things. If that Z is an OH, it would be a carboxylic acid. If that Z was OR, like an OCH3, then it would be an ester. And then you also have this HY, where Y is something very general, like probably the two most common ones we're going to see. It's going to be H2O, where you have the Y being an OH, or you're going to have Y being like an alcohol, right? So that would be CH3 with an OH attached, which would make that an alcohol. So those are probably going to be your two most common ones. And the idea here is that basically whenever these substitution reactions occur, Y and Z basically just trade places with each other. So for instance, if you were looking at the alcohol down here, the OCH3 would be what you would consider the Y part, and that would end up going over there. And whatever the Z part was, right, would end up going over here and being on your H. So again, general term here is this idea of a substitution reaction, and we're going to look at it in more detail on the next couple slides here. So this first reaction we're going to look at is probably one of the more important ones that you need to know, because it's going to show up quite a few different times, and that is that carboxylic acids react with alcohols to form esters and water. So carboxylic acid reacts with an alcohol, right? So that's an alcohol, right? Whenever you think of alcohol, you should be thinking of an OH group, right? So that's your O attached to an H, and then attached to that R part would be your carbon part. Forms an ester, that's where you have your C double bonded to O, bonded to your O with an R group there, and then obviously water over here. So in this case, the OR group right here is going to replace and trade places with that OH group. So the OR comes off of the H and it's going to end up over there. The OH group ends up over there with the H. So basically they're just trading places. So let's look at the reverse reaction of this, right? So the reverse reaction is when you have an ester reacting with water to form a carboxylic acid and an alcohol. So again, it's the same reaction we looked at on the previous slide, except in this case, it's going to go backwards. Now, the one key to this one is the hydrolysis of an ester. So hydrolysis basically means, so if you look up here for the word hydrolysis, this means breaking a bond with water. So breaking a bond with water. So that's going to be our definition of a hydrolysis reaction. Again, we're going to see that a few different times throughout the rest of the semester. And in this case, it said it requires an acid catalyst. So oftentimes you'll see, like for instance, H2SO4 written on top of that arrow. again showing that a catalyst works for that reaction. But again, it's just trading the places of the OH in that OR group to give us the two products. So this again just clarifies what we mean by hydrolysis, since it's cleaving with water, but I like basically this slide because it kind of gives us a good example of what the two groups are. So what I want to do here is say when you have your ester, so if I were to basically hide the products here, how would you know what the products of this reaction would be? Well, you're going to find your O and then the carbons that are attached to it, the carbons that are not in the double bond, and you're going to circle them. And then you're going to circle the OH, or H, not the H, but whatever else is there, the O and whatever else is attached to it that's not one of the H's. And then you're going to trade places. So in other words, this OH from the water is going to come over here to the ester, and it's going to bind to where that C double bond O is, right? And that's going to give us this product right there, which in this case is acetic acid, that 2-carbon long carboxylic acid. All right. And then in doing so, this other part here is going to leave and go bind with that H, and that's where you're going to have this alcohol. This one would be called ethanol, right? Alcohols are always going to end in OL. We skipped chapter 12 just for the sake of time, but a 2-carbon long alcohol would be ethane, right? 2-carbon long parent chain, and then the suffix would be OL for any alcohol. So in this case, you would have acetic acid and ethanol as your products in this hydrolysis reaction. Okay, so let's do a couple more practice problems with these reactions with carboxylic acids and esters. So the first thing is, whenever you're given a problem like this, you kind of want to look and see what it is you have, right? So in this one, what I'm going to do is I'm going to write up here that this is a carboxylic acid, right? How do I know that's a carboxylic acid? Well, based on the functional group, I see a C double bonded to O, bonded to an OH, which is going to make it a carboxylic acid. And then KOH is just going to be a base, right? That's a strong base. So that's one of those strong bases you had to learn back in the acid-base chapter when we talked about acids and bases. Anything that has like a metal, like a K or an Na or an Li, those are all metals on the periodic table. With that OH, that's going to make it a base, and that OH is really going to be the important part here. And whenever you see this, you should be thinking, I have an acid plus a base, right? Whenever you have an acid plus a base, the products for that are going to be water and a salt. So in this case, what's going to happen is the carboxylic acid is going to donate its proton. The base is going to have the OH. Those two are going to come together to form H2O, right? You could also imagine that as H bonded to OH. It's the exact same thing. Now, the other pieces are going to be all of that, and then the K. And what's going to happen with those is they're going to form a salt. And whenever we write the salt, we're just going to write it as K+, which is going to be the cation. And then we're going to write the anion, which is basically we're just going to copy that structure. And it's going to look like that. That's going to be your anion. I kind of misdrew up here a second ago. Whenever I did this, I should have also included this O in it all, right? Because that's the part that's not attached to the H. So you're going to end up with water plus the salt, which is going to be the two different pieces, which are going to be the K+ cation, and then the carboxylate anion, which is going to be basically CH3 right there, CH2, 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 C, O, O minus. All right, so again, acid plus base gives water, and then the salt would basically be both of these things combined. That would be your salt. Okay, your next reaction here, whenever we're looking at it, again, first thing that I like to do is identify it based on the structure. So this one is going to be an ester. This one is going to be water. So whenever you have an ester in water, what do? Well, whenever you see water here, the first thing I'm going to suggest is kind of rewrite this as HOH, right? Just in general, whenever you see water, rewrite it as HOH, because whenever we do these substitution reactions, right, this is how we looked at it. We said they're going to trade places, and it's going to be that OH that's trading places. So this makes it a little bit easier to visualize. So what we're going to do here is kind of circle the two different parts of the molecule. So I'm going to go here and say on my ester, remember whenever we looked at substitutions, it was going to be the O and everything attached to it that gets moved. And when I say the O and everything attached to it, is how do I know whenever I'm looking at this O here, do I circle to the right or do I circle to the left? Well, the rule here is you cannot circle through the carbonyl. So basically, what's going to happen kind of in more specific chemical terms is that bond right there is the one that's going to be broke. Your ester bond is going to be the one that's going to be broken. So whenever we look at this, what we're going to do is we're going to circle the O and whatever is attached to it that does not go through that carbonyl group. And then we're going to come over here on my water and we're going to circle that OH. So now my products are going to be the same two things, except those two green places are going to exchange themselves for each other. So we'll start with the HOH. Instead of HOH, it's going to be H, and instead of drawing the OH, I'm still going to draw the O, but then that O is going to be attached to the pentagon, right? So that's going to be the product. So it's going to basically be, another way you could see this written, you don't always have to draw, usually we don't draw the OH bond separately, but this and that are the same thing, okay? So that's going to be one product. Now the second product is going to be plus. The other thing we're going to make is we're going to go ahead and rewrite this part of this molecule, right? And then instead of drawing the part that's in green here, I'm going to add the OH to it. So let's first redraw that part. See, double bonded to O, bonded to CH2, CH2, CH3, and then instead of the O with the 5-membered ring, now I'm going to draw an O attached to an H. So in other words, what we did is we traded places. This OH that's right there got moved from there over there, and this got moved from there over to the water. So our two products for this would be an alcohol and a carboxylic acid. So again, remember that whenever you have an ester reacting with water, you're always going to form an alcohol and a carboxylic acid. Carboxylic. So those are going to be the two groups. So again, this takes a lot of practice to trade places with those two groups and to write these out. So do a whole lot of practice problems and you should be able to get the hang of it.